Good day and welcome. My name is MJ Swats. I am the Education Manager of the Cape Town Science Centre. And today I have the joy of taking you through how to choose an Expo project. It's really a guide, especially for those who are doing this for the first time. And when teachers are coming into having to look into doing Expo projects for the first time, there is usually this perception that it's going to be a burden. It's an overload. There's so much work to do, and it's enough to scare a person off. But this perception need not be the reality. I want you as the educator to not think of these Expo projects as something that you need to pull and carry like a heavy burden. You are not primarily the driver. You are the GPS. You are there to provide strategic input and guidance to the learner. It is the learner that is the primary driver of the Expo projects. So how do you really approach these Expo projects? How do you begin? The starting point, of course, is always with the idea. And any idea has to be executable. It's actually good to always ask the learner the question of, well, what are you actually going to do? But more important than an idea being executable, the idea must be something that they are passionate about. It must be personal. And that is vital because it has to be a project that the learner can take ownership over. It is their project at the end of the day. So if they can feel passionate about it, they are more likely to invest more of themselves in the project. So let's break down how to go from this idea all the way through to the project. And we have this flow that can actually guide you. The thing that I want you to remember, regardless of the ideas and how you construct them and all of that, what is Expo about at its core? At its core, it's really about developing critical thinking and developing critical and process thinking. It doesn't matter what your project is, what category it goes into, or what type of project it really even is. These are fundamental to all Expo projects. And it's really the thing that we try and bring out, try and get the learners to really take hold of, because that's where the real learning happens. That is the arena of discovery in the end. So let's begin to talk about each one of these in turn. Let's begin to break up the idea. It's very important that whatever the idea is, that it has to be a realistic, original, personal, understandable, focused, and time possible idea. Let's break that down. First of all, it must be a realistic idea, in that you can't choose an idea where the science doesn't necessarily even exist to support that idea. Now, I'm not saying that discovery is out of the realm of possibility. It certainly can be possible, but it's not the most probable thing to take place at ESCOM Expo. What I will often see happen with these projects is learners will take an idea, but it will be something that the science isn't developed. It's something that they've heard about before or seen on sci-fi, or they haven't really understood the science, or they saw a need and they wanted to address the need, but the way that they're going about it isn't very realistic. So one of the first things to do is to help them to develop a realistic approach to what idea they want their project to be about. It must be original. We're not in the business of making photocopying machines. We want learners to really take something that they can feel personal about, that is a reflection of them. It's not just going into a textbook, pulling out an experiment and redoing the experiment. You are missing out on the opportunities. Where's the critical thinking there? Where's the process thinking there? So we really try and encourage them to find ideas that are original. Understandable is also very important when trying to weigh out your ideas. Don't bite off more than you can chew. It's much better to take something that you can understand and fully explore rather than taking something so high level. You are setting yourself up for a great degree of frustration and probably misinterpretation too. It's like trying to see a grade six child coming into Expo and right off the bat doing a project on quantum mechanics. Now, there may be some that would be able to do it, but by and large, they are taking something that's so far above their level of comfort that they may actually get lost in that wilderness. So always keep in with areas that you could have reasonable understanding of. Now, I'm not saying only rely on what you know. This is also a place to go do research and grow, but don't go too far. Else, what's going to happen is you're just going to hit walls of frustration and you're going to lose your momentum and probably some of your motivation too. Keep it focused. That is vitally important. Many times they are too broad, and so to try and make a statement of proof, to try and actually prove something, to put an experiment together, all of that becomes very difficult because of how broad the idea is. So filter it down and focus it. And very important, make a time possible. If something takes 3 years to research, you're not going to get that done in 3 months. So make sure that you keep it within realistic time constraints. Time is especially one of the great stress factors. So if you are not careful with your time management, then you're going to add a lot of unnecessary stress into the process of doing your Expo project. When you are doing these projects, I have a list of questions that I like to encourage learners and teachers to go through to actually check if they have really thought about their idea, if they have unpacked their idea fully. Number one is I want you to ask the learner, what are they going to measure? It's not enough to just have an idea. Let's be practical about it. You have this idea. What is the thing you're going to measure? And what instruments are you going to use to measure it? And once you have that, try think about what the units of the measurement will be. I once had a learner that came and told me that she wanted to develop a device that could predict when a flood was going to happen. And I was like, wonderful. Okay, how would you do that? I would have this box. Okay, how does this box work? There was no thought. There would be a button on the box. So there was no idea of what you would make or measure or what the units of measurement would be. Like you're going to predict a flood before it happens. How are you going to predict a flood? What is your unit of measurement that you would read to say, no, a flood is coming? So asking these questions really helps you to make sure that the learners are still practical, because it's not enough to have an idea must be executable. There must be something that the learner does in the end. The problem with a lot of Expo projects, with science fair projects, my feeling is the way that they are portrayed in the media. That when you really look at it, you get these two levels of ideas that are portrayed. One is very rote, very algorithmic projects that are almost copy-paste of what's been seen before, like a bicarb vinegar volcano. It's not original. You're just demonstrating rather than investigating, and it's something that is in every textbook, every website. It is not a fully fledged, unpacked idea. Then you get the other ones on the other side where the idea is so advanced, the science doesn't exist for it. And the truth is, neither one of these are realistic depictions of Expo projects. The truth is, Expo projects are between that is where they in reality exist. It's not the carbon copy out of the textbook, and it's not the futuristic, the science hasn't been developed for it yet type of projects. It's the in-between bit. And something to really help you hone in on this is I want you to remember that it's better to have a simple idea and a spectacular method than have a spectacular method and a bad idea. So don't worry too much about doing the giant, flashy, it looks good on paper ideas. Rather concentrate on the process. Start with a simple idea and grow from there. It's a safer way to approach starting an Expo project. This is a good checklist to actually give learners to complete. And with this, they'll be able to determine if they've really thought of everything at each step of the way, to make sure that their idea is clear and achievable. So we can go through an example of a project to show you how you could use this list to actually unpack and double check that you have thought about your idea all the way through. For instance, let's take a project that is a scientific investigation. And this project, I've decided, is about biofuels. Now, what will I be investigating for this project on biofuels? I want to produce a biofuel from weeds in my garden. So that is, I'll be investigating how to do that. And what I'm hoping to find out is I want to find out if I can go and run a car engine using these biofuels that I've produced, which would be ethanol. So to do this, I'm going to produce my own ethanol, and then I'm going to measure how long I can run a car's engine off of this ethanol that I've produced. And I'll compare my biofuel, 1 liter of my biofuel, with 1 liter of commercial petrol. And I'll see which one can run an engine longer. To do this, I will need to use weeds and yeast, and I'll need to use the chemical apparatus within the school. I'll also need an old car engine for actually doing the engine test. Now, I can't do all of this without supervision and permission. So what supervision is required? What permission will I need to obtain? Well, first of all, I need permission for me to go take weeds out of people's gardens. You can't just go into someone's gardens and take things. Also, when I do the actual chemical experiment, I'll need my teacher to supervise that process. And very important, to use the old car engine. I can't just go and use a car engine. I definitely would need the permission of someone to go put my biofuel in that engine. And then what category do I think this will fit into? Well, this would fit into a chemistry category. So there I've been able to fully unpack my idea. I've been able to check, is it clear? Is it achievable? Is the time possible? It's a good way to calibrate your idea. And of course, there's multiple categories that your idea, that your project can fit into. What you will sometimes see is that the category that you have in the beginning isn't the category that you have at the end. ESCOM Expo for Young Scientists have about 13 different Expo categories. Some of these include scientific investigations, there's computer science, there is engineering, there is social science projects, there's mathematical projects. There's a whole plethora of categories so for a learner to actually choose from. Now, when approaching these categories, approaching these ideas, after you have unpacked your idea, you need to start to go and do your research. Now, this is a sand trap for many learners, where they see the research as the end of the project. Your literature review is not the end of your project, it is merely the start. I've seen a lot of learners that actually get stuck in this literature review stage. And when you come and see the end product, the end project, it's like reading a book report. They have reported on what we know, and that is about it. They have just related everything that is known, but they haven't done anything themselves. What did you measure? Didn't measure anything. Did you build anything? Didn't build anything. What did you do? You only read up and you reported. You gave me a book report. And that is quite dangerous, because if you have a book report, you can basically have an incomplete project. So you have a project where you didn't think through the whole process. So for instance, I can have a project where I try and take bottles of various different sugary drinks, and I look at the amount of sugar in each drink. So I look at the amount of sugar in that drink, and then I just display that. Now, because I've just displayed it, what I've actually done is a demonstration, not an investigation. So when I say what I'm hoping to find out, I didn't actually find out anything. I've merely measured the amount of sugar in drinks, and I've done this using a scale and bottles and sugar from the kitchen cabinet. But even when you try and put this in a category, it becomes difficult because they missed out on the fundamental part of any project. What did they investigate? What did they do? And it can't only be to demonstrate or to re-show someone else's knowledge. That is the crux. I don't want to see what someone else necessarily knows. That is the beginning of your project. It's not your project. Your project, I want to see what you know, what you have learned, what you are putting forth as your idea, as your hypothesis, as your solution. I want to see what you've done in the end. And so this is an example of an incomplete project, where the whole project is just more of a demonstration. Next, we need to look at how to take this idea and grow it into a statement. So you have your idea, you've done your literature review to learn all that you can know surrounding that idea. Now what you need to begin to do is you make your statement, which is either a problem to be solved if it's engineering, or a hypothesis if it's more on the scientific investigation side of things. And there is a difference between the idea and the statement. Your ideas are questions, they are areas of interest, they are things you want to create, they are problems you want to solve. So for instance, I've heard a lot about vaccines. What are vaccines? How do you make a vaccine? Can I make a vaccine at home? So that's questions and areas of interest. That is creation. Maybe you heard about quantum mechanics and you're interested in quantum mechanics, or nanotechnology. That could be an area of interest. It's just something that has piqued your interest. It's something that has created something of a question or something you want to achieve. It's the idea that's beginning to form. But then this idea has to get filtered through to an expectation of outcome. And that is what your statement is. Your statement is how you actually are expecting something to come out in the end. It's your expectation of your outcomes. So it's not a question anymore. It's a statement. And this is where your hypothesis comes in. And a hypothesis is not the same as a guesstimate. We like to sometimes try and explain kids, well, a hypothesis is like a guesstimate, and there's some truth in that, but fundamentally they are different, because your expectation of outcome, your hypothesis, is based on information. It's based on knowledge. It's based on looking at all you have learned. And on the foundation of this knowledge, I make this statement that I believe I can prove to be true. I expect this to be the outcome when I conduct my experiments. That is the difference between the idea and the statement. The idea, very broad in terms of you've got questions and areas of interest. You want to solve a problem, you want to create something, all of that. But it all has to get filtered through into one statement, which is your hypothesis, which is your expectation of your outcome. Next, we need to go and see the star of the show, and that is the experiment itself. It's what you have to actually do. Everything up to this point has just been preparation. Now we go and we actually do the experiment itself. And this is where a learner really begins to take ownership and make the project theirs. It is also the part that they can enjoy the most. Everything else before this, the literature review, doing your hypothesis, doing your ethics checks, everything like that, that's always not the most fun part of a project to do, but it's important. But this is where the enjoyment, where the project really comes to life and learners really begin to hit their stride. The first thing you want to do is make a project plan, and this is very important. Once you're going to do the experiment, how are you going to do the experiment? Make sure you've planned it out, because if you fail to plan, you're planning to fail. Also, make sure that you understand the process that you need to go through, especially with these scientific investigations. You have to prove your conclusion to me. And this is where a lot of learners begin to lose their way a bit. That what they have said as their idea and what they have said as their statement doesn't link to their experiment, and their experiment isn't linked to their conclusion. They haven't really met the burden of proof. They have said, I wanted to test A. They've done an experiment on B, and they say that, no, I've proved A. But you haven't proved A, you've proved B. That's what your experiment was on. So you need to make sure that your conclusion, that your burden of proof is linked to your aim. It's linked to that hypothesis. It's linked to your original idea that you had. Common mistakes that they will make is that the conclusion is only linked to the idea, but the data doesn't support it. We've just discussed that. There is no or insufficient testing. So they've done the experiment, but they didn't actually do any testing in the experiment. And then they want to say, I've proved my hypothesis. You haven't proved your hypothesis, or many times you haven't done enough testing to sufficiently prove your hypothesis. That is especially true with the social science experiments, where they often their sample size isn't large enough. They haven't used sufficient controls, and this is really where the variables of your experiment, the dependent, independent, and controlled variable are very important. It makes sure that there's good correlation between your variables, so that you can actually make statements to say whether something has been proved or disproved. Confusion between variables often happens, and and there's a confusion between things that are correlated and that actually cause. So the correlation and the causation is something that is not often well understood. So they are looking at one thing, but they are saying another thing. For instance, I once had a project of a learner trying to do a geothermal experiment. She dug a hole in the ground, she put a bucket of water in there, and she wanted to check if the bucket of water was going to be heated up by the geothermal energy of the earth. And she had put a motor within there, and then she was running this motor. Now, the motor was producing the heat, and so she wasn't actually able to prove this. But in her experiment, she didn't actually talk much about the heat. She was speaking more about the motor and how it was pumping the water and the rate that it was pumping. And then she makes a conclusion about heat. So not only were her controls not sufficiently in place, but she couldn't really correlate what she was talking about in the experiment with the point of the experiment in itself. They can also be sometimes very selective over the results. So I'll just cherry pick the results that will confirm my hypothesis. And the results are not often repeatable. It's been done once, but if you try and do the experiment again, it is not going to work. One of the major tenets of science is that all experiments, all results must be reproducible when you repeat the experiment. The conclusion must be based on the experimental data, not on the idea. No matter what your idea is, your conclusion in the end is based upon what you actually did in the experiment. You need to ask whether your hypothesis was proven correct or incorrect. And this is the thing, it's okay for it to be incorrect. You do not lose a single mark when you prove that your hypothesis was incorrect. It is just as good as a project that was correct. And you don't get marks for your idea, you get marks for your project. And your project really answers the question of what did they do in the end. It's the experiment, it's the recording of the experiment, it's the paperwork. All of that is what you get marks for. But purely having an idea is not enough. So make sure that this process thinking, the experiment, where really the critical and the process thinking comes out, forms the core of the experiment, not the idea. The idea is what got you started, and it grows into an experiment. And this experiment is the center stage. It's the heart of the project. There is often a misunderstanding or not a fully fledged conception of the experimental flow. So let's quickly go through that. You have your expectation of outcome, your statement, your hypothesis, and you want to go test this. To test this, you have the experiment. And the experiment ultimately is looking at cause and effect. If I do one thing, something else happens. And so by looking at this relationship of cause and effect, I can begin to understand what is happening. I can correlate the cause and the effect and make statements based upon that. Now, to really check that you have a good link between cause and effect, we need variables. And these are our scientific variables. They are the experimental variables. They are the independent, dependent, and control variable. Your independent variable is your cause. It is what we change. So for instance, if I was going to do an experiment asking, does the amount of time I spent studying improve my pass mark in the course? What is the cause? What's the thing that I choose the value of? What's the thing that I can change? It's the amount of time that I study. I choose, well, I'm going to study 5 hours a day. That's my cause. Your dependent is the effect. It's what the system, it's what the experiment gives back to you. It's what the response is. So if my studying time is my cause, my effect is my pass mark. And then the controlled variables are the things that I keep constant throughout. The things that I could keep constant in the in terms of the studying versus pass mark example are things like keeping it to one course, looking at your method of studying. So if I have 5 people studying, I don't want all 5 people studying a different course. They must study all the same course so that I know that it is not the course that is affecting my outcome, but the amount of time. Those are your control variables. The cause and the effect is really the heart of the experiment at the end. And then, of course, you also need to graph out quite often your independent and dependent variable. What I always tell my learners is think of the x-axis as the ground, and the independent variable goes in the ground. So if you ever get confused which one goes On the x-axis, just look for the one that goes in the ground. That's your independent variable, and then it makes it a whole lot easier for learners. Here are some examples where learners have really confused their what variable actually means. So, for instance, in this experiment, they said that the dependent variable is the end result of the experiment, and the independent variable is the method you are using. So they haven't fully understood their variables here. Here is a project where the hypothesis wasn't fully formed. They said that this project is the key for producing electricity by converting electricity from one energy to another energy. Also, to help the electrical supply of a country to reach the demand of electricity required by that country. This is closely related to an idea rather than a statement. Remember when we compared ideas versus statements? This is still their idea. And what they needed to do is express an expectation of outcome, a statement. That is what your hypothesis is. And they haven't done that. They haven't taken their idea and extracted from the idea what they expect the outcome to be, their statement in the end, which forms their hypothesis. So let us now look at one final area. What is the something new? And this is very important. This is something that was learned. And that for me, as someone that often goes to judge at these science fairs, it's the part that I love the most as a judge, because you will honestly be astounded by the new knowledge, the ingenuity, the creativity of these learners. It's a wonderful time even for us to keep on learning. And also, just on that point, never feel pressured that you always have to know more about every subject that you are helping your learners with. As a teacher, you're going to have many different projects that you need to oversee, and you can't be expected to be an expert in every field. There are always those that you can reach out to for help, but it's more the process that you need to actually guide. It's okay not to know everything. With the learners, with the something new that they do, it's important that they reflect, record, and improve. The improvement is especially important when you look at your engineering projects, where they have to do prototypes. This is something that I fundamentally believe, that science that is not communicated is science not done. I want to introduce to you one of my favorite chemists in history, Carl William Scheele. He was a Swedish chemist, and he actually discovered many chemical elements long before the people that were credited with their discovery, the most famous being oxygen. Joseph Priestley was credited with the discovery of oxygen, but we've actually determined historically that Carl William Scheele discovered oxygen 2 years before Joseph Priestley. The reason that Joseph Priestley gets the credit is because he published. Carl William Scheele was slow to publish, slow to communicate. And this is an important point, that communication, both verbal and written, forms an important part of a science fair project. And that is why the secret to a successful project is a project book, is a journal. Every idea, every thought, everything that they learn, they should learn to record it from the beginning. So some final thoughts I want to quickly share with you. Always remember to keep it simple, focused, and achievable, both the project and the idea. That it's not about being correct, but it's more important to be thorough. You will get much better marks and you'll actually enjoy the process more and get more out of it in the end. Concentrate more on action and recording. Don't spend too much time on ideas and then have no time left for actually doing something. The action, what the executable part, what the learner actually does, should always be the heart of their project. Don't try to do it yourself. Always reach out. There is always experts willing to help, experienced judges willing to give a bit of guidance. So don't feel stuck working on your own. Reach out. The early bird always catches the worm. So with this, the earlier you start your projects, the better it is. It helps to start earlier, because the later you start, the higher the pressure becomes, and then you begin to lose out on some of the nuances that this process is supposed to bring out for both the learner and within the project. The biggest advice that I can give you is to become a judge. If you really want to grow and understand more about science fair projects and how to approach them and how to be a good mentor, become a judge. Use the judging sheets. They will guide you, and they really are a useful calibration tool. And ensure that the ownership stays with the learner, not the parents. You'll see, especially with the engineering projects, parents love to sometimes take over. They are welcome to have input, but the project ultimately has to belong to the learner in the end. And don't be rigid. Things are going to change. Sometimes a project will start in one category and will end in another. Sometimes even the idea of the project evolves over time. That is all acceptable. So thank you very much for your time, and I wish you all the best for your ESCOM Expo projects this year. Thank you.